In this lesson, we are going to be talking about simple machines. So, by the end of the lesson, you should be able to list the 6 different types of machines. You should be able to calculate mechanical advantage. You should be able to use the work input and output equations. You should be able to calculate efficiency and identify the 3 different classes of levers. So I just wanted to go through a little bit of a reminder on what work and power are, just in case they come up in any of the equations or problems that you guys have to do on your homework. So what is work and what is the equation for it? So remember that work is the amount of force that is applied on a load over a certain amount of distance, for a certain amount of distance. So the equation for work is work equals force times distance. And power is the amount of work done in a certain amount of time. So the equation for power is power equals work divided by time. All right, so now what are machines? Well, you're probably thinking, well, it's my lawnmower, it's my snowmobile, it's my four-wheeler. Yes, it is. These are devices that make work easier. So now we have fancy lawnmowers that we can ride, we can push, they're self-propelled, and all of these fancy things that are on your lawnmower nowadays. But you may have in your garage, or your parents may talk about these old grass cutters that they had that you had to push, there was no motor, and it cut the grass just by propelling a bunch of blades in a circle. So what are some of the forces that are involved in machines? Well, we've got 4 here. We've got an effort force, an effort distance, a force of resistance, and a distance resistance. So effort force is labeled as Fe, and this is the force that is being applied to the machine. So when you think about it, you think about it as the amount of work, the amount of force that the machine is doing. Effort distance, we symbolize this with a dE, and this is the distance that the machine moves. Force of resistance, or resistance force, we symbolize this with an Fr, and this is the force of the load moved. So basically, this is just the weight of the load, whatever that may be. And distance resistance, this is symbolized as Dr, and this is the distance the load moves. So in some of the machines that we talk about, the effort distance isn't going to be the same as the distance, as the resistance distance, that even though you may think it's going to be, because in a wheelbarrow, the resistance distance and the effort distance are probably going to be pretty close to the same. But in like a broom or crane, the effort and resistance distance are going to be pretty different. And we'll talk more about that in the labs that we do. So now let's talk about input, output, and mechanical. Work input is the work done on the machine, and we symbolize this with a Wi. Work output is the work done by the machine, and we symbolize this with a Wo. And mechanical advantage is an equation that we can use to figure out how well the machine can do its job. So MA is equal to resistance force divided by effort force. So when you're calculating mechanical advantage, you're going to take whatever your resistance force is divided by whatever your effort force is. And in this case, there isn't going to be any units for the number that you get, because when you are dividing the units by each other, they're going to cancel out. It's just like taking 1 divided by 1. They end up canceling out, and you end up getting a number of 0. So let's do some practice. What is the mechanical advantage of a machine that has a resistance force of 200 newtons and an effort force of 100 newtons? So remember, the equation that I just showed you is MA equals force resistance divided by effort force. Okay, and we don't know what MA is. That's what we're looking for. We know that resistance force is 200 newtons, and we know that our effort force is 100 newtons. So now if we put that into the equation, it should look something like this. So then you're going to take 200 divided by 100, and your mechanical advantage for this machine should be 2. So in some cases, you may be given extra information. The only thing you need for this equation is the resistance and effort forces. All right, so now let's figure out how to calculate work input. To calculate work input, we use the equation WI, which is work input, is equal to effort force times effort distance. Because remember, those are things that the machine does. So effort force is the amount of force that the machine does, and the effort distance is the amount of the distance the machine goes. So work input is calculating the work on the machine. So let's try this problem here. If the effort force is 100 newtons and the effort distance is 4 meters, what is work input? So we're looking for work input. It said our effort force was 100 newtons and our effort distance was 4 meters. So if we plug that into our equation, it's going to look just like this. So then you're going to take 100 times 4, and you should end up with 400, and your unit is going to be joules because this is work. And remember, we always label work in joules. So to calculate work input, you need effort force and effort distance to come up with the answer. And now we're going to talk about how to calculate work output. So the equation for work output is WO equals resistance distance times resistance force. And again, work output is what the work that the machine is doing on the load. So that's why we're using resistance distance and resistance force, because these are related to the load. So let's try this practice problem. So if the resistance force is 200 newtons and the resistance distance is 0.5 meters, what is the work output? So we are looking for work output. It said our resistance force is 200 newtons, and it says our resistance distance is half a meter. Okay, so if we put this into our equation, it should look like this. And if we go ahead and calculate that, you should get a work output of 100 joules. All right. Now let's talk about efficiency. So the efficiency of a machine compares the work input and the work output. So it's trying to figure out, well, how efficient is this machine at doing the job required? So to calculate the efficiency of a machine, we take the work output divided by the work input and multiply by 100, because efficiency is a percentage. And the less friction that is inside a machine, the greater the efficiency, because the gears inside the machine, anything like the pistons in the engine, and all of those pieces then don't have to try to work harder to overpower the friction. So that's why when we are thinking of our cars, we put oil in our motor because we're adding a lubricant to reduce the friction so the pistons can move in and out pretty quickly. All right, so we're going to use the work output and work input from the 2 previous practice problems to figure out the efficiency of this machine. So our work input was 400 joules. Our work output was 100 joules. So we need to put those in our efficiency equation. So our efficiency is equal to 100 joules divided by 400 joules, which gives us 0.25. Then we have to multiply that by 100, which will get you 25%. So the efficiency of this machine isn't very good. It's at 25%. All right, so now let's talk about the 6 different types of simple machines. We've got the lever, the wheel and axle, the inclined plane, the wedge, the screw, and the pulley. You may have talked about these in middle school. So the only one I'm going to go into depth on is the lever. That's because we're going to talk about the 3 different classes. But the others, I'm just going to show you a picture, and I'm going to just talk about them pretty quickly and then go into the recap for the lesson. So the lever. This is a bar that is free to pivot or move about a fixed point when an input force is applied, so when an effort force is applied. And the pivot, we call this a fulcrum. So this gray triangle here is the fulcrum on this lever down here. And like I said on the previous slide, there are 3 different classes of levers based on the positioning of the effort force, resistance force, and the fulcrum. So now let's talk about those 3 different classes. Well, a first class lever has the fulcrum between the input and output forces. So it's between the effort and the resistance force. So if we were to draw what a lever would look like, a first class lever would look like, your fulcrum would be somewhere in the middle. Your input force or your effort force could be on one side, and your resistance force or your output force will be on the other. And these forces could be switched. It doesn't really matter. As long as the fulcrum is between the 2 forces, it's a first class lever. A second class lever has the output force or the resistance force between the input force and the fulcrum. So between the effort force and the fulcrum. So let's draw that. So here's our fulcrum. It says our output force is between our effort force and our fulcrum. So our resistance force is going to be here, and our effort force is going to be there. Okay, so now let's talk about the third class lever. Well, the third class lever has the effort force between the fulcrum and the resistance force. So now your fulcrum is here. Your effort force is here, and your resistance force will be down here. All right, so the main thing to take away from this slide is that the different classes of levers, the way to tell them apart is where the fulcrum is and where the forces are. So if the fulcrum is in the middle, it's always going to be a first class lever. If the fulcrum is near one of the ends, it could be a second or a third class. So in these two cases, you're going to have to figure out what force is where. So now let's use these pictures to identify each class of lever. Let's talk about the scissors. So we've got the fulcrum in the center. Well, as I said on the previous slide, anytime the fulcrum is in the middle of the two forces, it's always going to be a first class lever. So a scissors is a first class lever. All right, now let's talk about the wheelbarrow. So we've got our fulcrum as the wheel. Our input force or effort force is all the way on the end, and our resistance force is in the middle. So whenever the resistance force is in between the fulcrum and the effort force, that means it's a second class lever. Now, let's talk about the last picture. This is a broom just like any other broom you would use at home. Your fulcrum is going to be your hand at the top here. And your effort force is you applying the force to the broom with your other hand. And the resistance force is going to be the broom wiping on the ground. So now you have the effort force in between the fulcrum and the resistance force, which would then make the broom a third class lever. So these are three common items that you could think of that are identified as levers and are one of the three different classes. So now let's talk about the other simple machines. Let's talk about the flag first. So you're probably already thinking, well, I know what simple machine this is, and you're probably right. This one would be a pulley, because this yellow string here, you're going to pull on this, and you're going to pull down on that, which then causes the flag to go up. So there's a wheel here and a wheel there that allows this to happen. So this would be a pulley. Now let's talk about the mountain. Well, this mountain is an example of an inclined plane. It's when something goes from one elevation to another, or one height to another. So your starting point is somewhere way down here, and your ending point is somewhere way up here. They're at two different elevations. Okay, let's talk about the next picture. We've got a wedge inside a tree. Just like I said, this is a wedge. A wedge is typically triangular and it's used to pry things apart. So when you think about a wedge, think about a triangle-shaped item that is used to wedge something apart. Next we have the screw. So the screw is something that is used to turn, and it has an inclined plane on it that allows it to dig in. And finally, we've got the screwdriver. This one is considered to be a wheel and axle because the bottom part of the screwdriver here is the axle, because when you turn this, this turns as well, just like the wheel and axle in your car. So these are the 6 basic machines. On your test, all I would require for this is to be able to identify the different types of levers and maybe identify definitions or basic definitions for them. We will be doing labs on the pulley and the inclined plane, as well as the lever, but the screw, the wheel and axle, and the wedge, after the worksheet, this is about as much as I'm going to cover for this. So now let's do a little bit of recap. We know that machines make work easier for us, and we know that the equation to calculate mechanical advantage for a machine is the resistance force divided by the effort force. We know that the equation for work input is WI equals FE times DE, and we know that the equation for work output is WO equals FR times DR. We know that the equation for efficiency is WO divided by WI multiplied by 100 to get a percentage. And we know that the 6 different types of machines are a screw, an inclined plane, a pulley, a wheel and axle, a wedge, and a lever. And we also know that there are 3 different classes for levers. So this is the end of our lesson. If you have any questions, please put them in your weekly journal. Otherwise, have a great day.